Welcome to the Cool Part Show, the show about interesting 3D printed parts. I'm Stephanie. I'm here at NASA Langley Research Center. Wind tunnel testing is a critical activity for NASA, and here at NASA Langley, they do all kinds of testing for everything from planes and helicopters to planetary entry vehicles. To have a successful wind tunnel test, you need two things: a scale model of the craft and also a way to capture all of the data about how it's behaving inside the wind tunnel. There is a device used to both hold the model and a lot of the delicate instrumentation needed to capture that data that is now being made additively. 3D printed wind tunnel balances on this episode of the Cool Part Show. Thank you for tuning into the Cool Part Show. If you like this episode, help us out, subscribe to the channel, hit the bell icon to get notified about new episodes. Today we are in Hampton, Virginia at the NASA Langley Research Center, standing in front of one of their wind tunnel facilities to learn about 3D printed wind tunnel balances. So these devices are used to measure the forces and moments that a model experiences inside one of these wind tunnels. The one that I have here is 3D printed stainless steel. It's been finish machined, but it's missing all of the instrumentation it would need to actually go into the wind tunnel behind me. Back in the early days of aerodynamics, wind tunnel balances really did look like what you'd picture as a balance, like a big set of scales. But as the manufacturing methods have improved, as the sensors have changed and gotten smaller, wind tunnel balances have gotten smaller and more compact as well. Today, most of the ones used here at Langley have been made through some form of machining. However, they are now starting to experiment with making these additively. So to tell us a little bit more about this facility and the role of wind tunnel balances, I want to introduce our expert for this episode. This is Devin Burns. He is an advanced manufacturing and design engineer here at NASA Langley. There aren't a lot of engineers out there focused specifically on force measurement and wind tunnel balance design, but Devin is one of them.
NASA Langley has a diverse array of wind tunnel facilities spanning many speed regimes from the subsonic to the hypersonic. And as a result, we see a wide variety of testing applications. For instance, we'll see commercial aircraft, helicopters, spacecraft, where we're simulating entry into both Earth's atmosphere and other planetary atmospheres. So our group designs wind tunnel balances, the mechanical design, and then we work with contract partners to manufacture, instrument, and calibrate the balances for use in NASA Langley's wind tunnels. We're able to do that by basically doing a very detailed mechanical design where, for instance, if we're trying to measure normal force, we will isolate an area on the wind tunnel balance where we're going to locally target a certain amount of strain to develop. At that location, we would then put what's referred to as a strain gauge, which is a device that's going to convert strain into an electrical signal, voltage that we can measure with a voltmeter. So by doing that, we can relate electrical output to force applied. And then we develop a math model that relates the two, so that when we're in the wind tunnel and measuring these voltages from the balance, we then can use our math model to understand the forces and moments being applied to the wind tunnel balance.
So wind tunnel balances today are these metal devices fitted out with all of this instrumentation. They are complicated, they can be delicate, but they also need to be strong and durable because they're part of the hardware of this system as well.
So in addition to being a sensor, it is also a structural element. Basically, the wind tunnel model is suspended on the end of the wind tunnel balance, and all the loads going into the model are transferred through the balance. Therefore, it's got to be able to tolerate those loads. So there are stress requirements. There are also deformation requirements, and sometimes we have structural dynamic requirements as well. Our wind tunnel balances vary, particularly in size and load carrying capacity. For instance, we've got some balances that are roughly a 1/2 inch diameter, and we've got internal balances that go all the way up to 5 inches in diameter. And within that size span, we'll have load carrying capacity of only a few pounds up to about 12,000 pounds of normal force.
So wind tunnel balances can vary a lot depending on the forces they're meant to measure, the requirements of the model, but they are reusable. The same wind tunnel balance might be appropriate for both a helicopter body and a planetary entry vehicle, just depending on the specific requirements. So NASA Langley maintains a library of about 300 or so wind tunnel balances that have been manufactured over the years. They're kept in operational order, they can be pulled from the shelf and used as needed whenever the requirements match up. But the difficulty is producing new wind tunnel balances, and a lot of that comes from the lead time and the requirements of the process that has been used to make these balances for about the last 6 decades.
Wind tunnel balances have primarily been made one way, at least the NASA Langley wind tunnel balance, since the 1960s. And what's significant about the 1960s is that's when the availability of electrode discharge machining really began to proliferate. We can do a lot of unique and complicated cuts with plunge EDM, which we really rely on. And that's worked quite well for us, with the one primary downside that EDM is a quite slow process. The material removal rates are quite slow. So it typically takes about 1 year to manufacture a typical wind tunnel balance.
So EDM, electrical discharge machining. This is a form of machining that uses electrical charges to melt and remove small bits of metal at a time. For plunge EDM, you need an electrode, a tool that is basically the inverse of the shape that you need to make in your workpiece. And so tooling up for this process and then the actual pace of plunge EDM itself adds a lot of time to the manufacturing. But around 2017, Devin learned of a different possible way to go. He was doing a literature review and encountered an SBIR, Small Business Innovative Research proposal, that resulted in a simple 3D printed wind tunnel balance. That success and consulting with some experts in additive manufacturing led his group to realize that additive manufacturing, specifically laser powder bed fusion, could be a better method for manufacturing these instruments. So Devin and his team worked with additive manufacturing service providers across the United States to first get coupons for material testing and then to start to develop what a 3D printed wind tunnel balance could look like and how it could be manufactured. It wasn't necessarily a simple one-to-one process. You couldn't exactly take a plunge EDM design and just move it into a 3D printing scenario. There were some challenges, some things that they needed to work out along the way.
There were two primary challenges we had to overcome in terms of manufacturing balances additively. The first was residual stress issues, particularly as we got to larger diameter balances. So either the balances would deform beyond a level we were comfortable with, or we would get residual stress cracks. And that really was fairly problematic for a while. We spent quite a bit of time trying to figure out a solution to that, working on our build support strategy, and ultimately came to a solution that seems to have worked quite well for a number of balances now.
Overcoming the stress cracking issue meant experimenting with the orientation of the balances in the printer, playing around with the support structure strategy, but eventually they got to something that worked. It took about 2 years to go from that first idea to the first additively manufactured wind tunnel balance. But there was still work to be done. There's a whole qualification process necessary for any balance to get into one of these wind tunnels.
There was no clearly defined process for additive structural parts. So we basically had to create that, and that was as much a technical challenge as a organizational challenge, trying to get the right people together to work on this problem, and then find the right people to approve the proposal we put forward.
Developing the qualification process took another year or two. It actually resulted in a framework published in a paper that we can link in the show notes about how to qualify a one-off structural component like this. At this point, there's been about 6 additively manufactured wind tunnel balances made. They've been tested in the lab. Unfortunately, none of them has run in the wind tunnel just yet, just because this particular facility is down for maintenance. But when it's back online, that'll be hopefully one of the first things that gets to run. So it takes about 4 to 6 weeks to have a new wind tunnel balance 3D printed. Of course, there is still finish machining, all of the instrumentation, the calibration process that needs to happen, just like any other wind tunnel balance. But compared to that lead time of maybe up to a year for an EDM version, that is a huge time savings. And so Devin and his team anticipate that many additive balances will be made in the future just for that lead time savings alone. However, it's also been possible for them to improve the design of some of these balances thanks to the geometric possibilities of additive manufacturing. Flow-through balances are one possible application.
A flow-through balance is just like another wind tunnel balance in the sense that it has to measure the forces and moments applied to it. But in addition to that, it has to pass high-pressure gas through the balance and out into the wind tunnel model for the wind tunnel model to use for some sort of aerodynamic phenomena that it wants to simulate. So for the particular application we designed this balance for, we were building it for a Mars entry vehicle for the reaction control system testing of that vehicle. There's ground testing that occurs to help validate computational fluid dynamics models. So that ground testing historically had consisted of 2 test entries, one that required a flow-through balance that had no thrust measurement capability, and a second test entry where we used a non-flow-through balance with thrust measurement capability. So what we've been able to do with additive is consolidate that test matrix down to one entry because we've been able to design a flow-through balance with thrust measurement capability, and that's really been enabled by the design flexibility offered to us by additive manufacturing.
So there's still some more work to do. Devin says that understanding the fatigue properties of additive parts will be key to really helping this application advance in the future. So this cool part is a wind tunnel balance. Other modern balances have been manufactured through a machining and joining process or plunge EDM, which can be very long and time consuming. NASA is now using additive manufacturing, specifically laser powder bed fusion, to start to produce these balances, primarily for the lead time savings. They can get one of these balances made in a matter of weeks rather than maybe up to a year with EDM. And it's also allowing them to improve the balances, to add additional functionality that wasn't possible previously. So that's it for this episode of the Cool Part Show. Thank you, Devin Burns. Thank you to the NASA Langley Research Center for having us. If you'd like to see other parts made by and for NASA, check out the links in the show notes to some of our other episodes. And if you have a cool part that you'd like to see featured, maybe you'd like us to come film in your facility, email coolparts@additivemanufacturing.media. Thanks for watching.